In this video, I'm going to present about the objective function design in optimization. So as we know, one of the important element in optimization using meta-heuristic approach is the objective function. Okay, so the definition of objective function is a mean to maximize or minimize something, or in a simple word, it is a formula that calculate the quantity or calculate the measurable indicators that we want to optimize. So it will determine the fitness value or fitness function for our problem. Okay, so this is the general guideline in order to determine or establish the objective function. By the way, for the objective function, sometimes is also being known as fitness function, optimization objective, and so on. So basically, it's refer to the formula that been used to calculate the indicator or the quantity to be optimized. Alright, so again for the guideline, okay, first of all, we try to understand the problem. So clearly define the problem and its key variables, constraint, and objective. Then define the goal, okay, determine the specific metric or outcome that we want to maximize or minimize. So we must understand, okay, our goal in the optimization. If we want to minimize or maximize something. Then number three, we identify the variables, okay, relevant variable that influence the objective. Then we quantify the objective, establish a mathematical measure to evaluate the objective, then formulate the objective function, express the objective function as mathematical equation or formula, then consider the constraint, validate and refine and optimize the objective function. So these are the general guidelines. Okay, now we will look at the common way, okay, how to establish or how to formulate the objective function. Okay, so basically there are three common way how we can formulate objective function. Number one is we directly take or cite from literature source, okay, maybe from the textbooks, from the academic journal, and so on. So we can utilize the function or the model that has been reported in the journal. So that is number one. Number two is by using the experimental design. Okay, I will explain later. Then finally, by deriving the function or the formula by our own. Right. So this is an example of objective function that we can take from literature. Okay, so in academic or the research journal paper, normally they will present a model, okay, a mathematical model or mathematical function that intended to be minimized or maximized. So we can directly utilize this model. Okay, this is the first option. Okay, this is another example, the model from the literature. So we can utilize this model as long as we really understand all the given notation, the given calculation, and so on. Okay, then the common objective function from literature is generated by using a certain design of experiment. Okay, for example, in one paper that reported a set of experiment that has been conducted like this. So they tested the different variable value, okay, at the different level, and later on they come out with the mathematical model like this, so we can utilize the model. Okay, so that is the first option where we utilize the objective function from literature. Basically, it's not limited to the research paper. We can utilize the objective function or the formula that has been reported in the textbooks. For example, in the machining, so we have the calculation how we can uh, calculate the machining time, for example. So we can utilize that particular model. Okay, but remember, when we utilize the objective function from literature, if we are doing the postgraduate research, that one is not considered as the novelty or contribution, since you are utilizing the existing model that has been published or reported in the literature. Okay, so maybe the contribution might be on the novel approach, novel optimization approach, in order to optimize this function. Okay, then the second approach is by using the experimental design. So I believe in engineering or science, most of us will involve in experimental based research. Okay, so basically we can formulate the function, okay, the objective function from experimental table. Okay, for example, in this problem, okay, we are conducting the machining experiment using EDM drilling. Okay, whereby we already identified the response and variable for this problem. So the response or the output variable that we want to measure is the material removal rate and hole diameter, whereby the variables are the pulse on time, pulse off time, and also the peak current. So we want to investigate how these three variables will influence the response here. So that is normally the experiment that we are conducting here in the research. Okay, then we will conduct the experiment as usual. So of course, for the studied parameter, we have a certain level that we want to investigate, and we have a design of experiment table. So based on this table, we will conduct the experiment and measure the MRR or material removal rate and hole diameter, and we need to complete this experiment. Then after that, when we analyze the results, okay, so we also can generate or uh, establish the mathematical model using regression analysis, for example. Okay, so based on the experiment that we have conducted, so basically we can come out with the mathematical model by using regression analysis or other type of statistical analysis that will provide the mathematical model. Okay, for example, for these two indicators, so we can come up with this mathematical model. So MRR, so have a certain constant, okay, then also the coefficient multiply with related parameters and so on. Okay, so this is the standard way how we construct the objective function or mathematical model from the experiment, right? This is the second approach. And finally, we can derive our own objective function. Okay, but in order to derive our objective function, we required for a depth knowledge of the problem that we are dealing with. Okay, for example, if we want to optimize a certain mechanical design problem, so we need to formulate the problem according to the mechanical design knowledge. So in this situation, we need to have a required knowledge or the depth of knowledge that can be used to formulate the problem. Okay, so some of the example of the problem is like mechanical design problem. So maybe we have a certain statics or dynamics problem that we want to optimize. So we need to formulate the problem by using the knowledge that we have. Another example is maybe the cost profit decision making. Okay, maybe in the production system, we want to identify the number of maybe the raw material that come out with the maximum profit, for example. So we need to have the knowledge in that, and we can formulate the problem. So another example is in a production planning, the scheduling, and a lot more other problem, okay, based on our expertise. Okay, so this is the uh, steps that required, okay, in order to derive our own objective function, okay, especially based on the manufacturing system or industrial engineering problem. Okay, first of all, we need to understand the problem. So we need to have an appropriate understanding of the problem, and then normally we will use a sample problem and try to make manual calculation. So during the first step, understand the problem. We already supposed to have an idea what we want to minimize or maximize, or what we want to optimize in the problem. Then by using a sample problem, we try to make manual calculation. Okay. Then from there, we can identify input and output. Then next, we standardize the calculation method, and finally establish the model in the programming platform that we are familiar with. Okay, so I will give an example here. Okay, for example, a single machine scheduling problem. So we first of all, in the first step, we try to understand the problem. So we have a set of n job to be processed on a single machine. So we have a set of job, okay, to be processed on a single machine. So the aim or the goal of the problem is to minimize the lateness. Okay, we want to minimize the lateness in processing or in the delivering. Okay, so that is we understand the problem. Then the second step is we try to use a sample problem and make manual calculation. Okay, for example, okay, we have a data here which consists of job J1 until 6. So means that we have a 6 job to be processed on a single machine here. PJ is the processing time. So processing time for job number 1, 2 until 6. Then the due date, or DJ here, is representing the due date. So let's say the time here is in hours, for example. So job 1 is requiring 10 hours to be processed, and it must be delivered at the 15 hours. Okay, on the 15 hours it must be delivered. Okay, so this is the example of the data. So we try to solve this problem by using a manual calculation first to get to really understand the step in order to calculate the lateness. Okay, the lateness. Right. So this is we use a manual calculation. Okay, then let's the job processing sequence. Okay, in this example, we assume that the job processing sequence is 2, 3, 1, 5, 4, 6. Okay, so we sort the job here. Okay, we sort the job here according to this sequence. So 2, 3, 1, 5, 4, 6. So means that the PJ, or the processing time, and DJ, or the due date, will following the job. Okay, for example, job number 2 required 3 hours and the due date is on the 6 hours. So it will be located at the front here, because job 2 will be processed first. Okay, then it's followed by job 3. So the data of job 3 also will be located at the second position. 1 is located on the third position, and so on. Okay, so this in this step we basically sort the data according to the job processing sequence. Then the next step, we calculate the completion time, okay, CJ, and also the lateness, LJ. Okay, so we calculate the completion time. Okay, this is the original sorted table, okay, from here. Okay, so for job 2 is required 3 hours. Okay, so it will be completed. Okay, if this is the first process, so it's supposed to be completed at the third hours. Okay, then the next process or the next job, which is job 3, requires 4 hours to be completed. Okay, so 3, okay, the completion time of the job number 2 plus with 4 is equal to 7. So means that job 3 supposed to be completed at the 7th hour. Okay, then for job 1 required 10 hours, so 7 plus 10 is equal to 17. Okay, so job number 1 will be completed at the 17 hours. So remember, CJ is the completion time. Completion time in a cumulative uh, time duration. Okay, then LJ is the lateness. Okay, so lateness means the completion time, CJ, minus with DJ, the due date. Completion time minus with dj. So 3 minus 6 is equal to minus 3. So the lateness here is minus 3, means that this job has been completed 3 hours earlier than the due date. Okay. Then for job number 3 is completed at the 7th hour, but it must be delivered at the 9th hour. So means that 7 minus 9 is minus 2. So this one is also completed 2 hours earlier than the due date. Okay, for job number 1, the third one, so it has been completed on the 17 hours, but it must be delivered at the 15 hours. So 17 minus 15 equal to 2. So means that for job number 1 is already 2 hours late from the due date. Okay, the same things also for job 5, 7 hours delay. Job number 4, 12 hours delay, and job number 6, 11 hours delay. Okay, so from here is basically the maximum lateness. So we take the maximum value from LJ here, which is equal to 12, and the average lateness is the summation of LJ divided with number of jobs, which is 6, so equal to 4.5. So means that the average lateness here showing that on average the job will be late. Okay, so that is the method how to calculate the completion time and lateness. Okay, all right, so previously we are on the second step, which is use sample problem and make manual calculation until we can calculate our targeted indicators. Okay, then number 3, we identify input and output. So again, for this problem, the objective is to minimize the lateness L. The input is scheduling data, so we need to have the scheduling data. Then processing sequence, job processing sequence. So for the data, it consists of number of job, processing time, and due date. So this is the the first input, which is the data, the scheduling data. And the second input is the job processing sequence. So that is 2 inputs. So we have our model, and the output from our model will be average lateness. So we want to measure lateness based on the average lateness. Then step number 4, we standardize the step. Okay, based on the manual calculation that we did earlier, so we try to standardize the step. Okay, so first we establish job processing sequence. Okay, job processing sequence, this one. Okay, job processing sequence. Then We sort processing time and due date according to the sequence here, which has been conducted in this step. So we have the data, we have the processing sequence, and we sort the data according to the processing sequence. So that what is being meant by the second step. Then number 3, we calculate completion time, okay, as being calculated in this table. And number 4, we calculate the lateness. So we calculate the lateness as well. And finally, we calculate the average lateness as L bar. Okay, this one L bar. So we calculate the average lateness. So this is the standardized step in order to calculate the average lateness in this example. Then number 5, the next step is to establish the model. So we calculate, or we create, or we code the step that has been identified earlier in the programming platform. For example, in this one, we are utilizing MATLAB. Okay, so step number 1, we establish job processing sequence. So for example, our sequence is like this: 4, 3, 6, 2, 1, 5. Okay, then step 2, we sort pj and dj according to s. Okay, sort pj dj according to s. So we are sorting this data. So from the s data, this is the raw data. Okay, like this one, like this data. Next, we sort the data. So we sort the data following the sequence here. So now it being known as sort data. Then step 3, calculate completion time. Okay, so here we calculate the completion time. Step number 4, we calculate the lateness. Then we can identify the maximum lateness. And step number 5, we calculate average lateness. Okay, so this is the model that has been created earlier, okay, following the standard step that we set, step 1 until step 5, to calculate average lateness, okay, based on this sequence. So based on this sequence, so if I run this one, so I will get the output table. So the first column representing the sequence, then this is a CL, okay, completion time, and the last one here is representing the lateness. Okay, so the maximum lateness that taken from this table is 21, okay, maybe 21 hours. Okay, then average lateness, so again we calculate the average from the lateness here, 4.66. Okay, so this is the output for the input of the sequence here, and also the scheduling data. All right, so now this is the maximum lateness and average lateness for this sequence. Okay, so let's say right now I'm changing the sequence. Okay, let's say 1, 2, 3, 4, 5, 6. So if we look at the average lateness later on, suppose it will be changed. So right now I will run. Okay, so now the average lateness is 6.3, worse than the previous sequence. Okay, so again, if I change this sequence, let's say 6, 5, 4, 3, 2, 1. Okay, so now the average lateness will be 7.16, okay, much worse than the earlier. Okay, so now the function or the duty of algorithm is to find the most optimum sequence S here that come out with average lateness. Okay, and again, as has been discussed in the earlier video on the combinatorial optimization, most of the metaheuristics algorithm are developed or using the continuous representation. Okay, so now we need to know how to what we call convert the continuous representation into permutation representation like this. Okay, so for that purpose you can refer to the earlier video uh, how we can convert the continuous representation into a permutation representation like this. Let's say if I want to test for the random input based on the sequence, so I will put rand permutation 6. So suppose it will create the uh, random uh, sequence, okay, random sequence based on the uh, given instruction here. Okay, so now the sequence is 6351, average lateness 6.16, 8.8, 6.8, 9, okay, 5.5. Maybe so far I think this is maybe the lowest, 5.5. So okay, this is I think the lowest one, 3.8. So far 3.8 here is the lowest one. Okay, so for a simple problem like this with six job, maybe we can use a trial and error like this. Okay, but if we have let's say a 10 job or maybe 20 jobs, okay, the number of possible solution will tremendously increase. Okay, for 6 job like this, okay, the possible sequence will be equal to 6 factorial, okay, which is equal to 270 possible sequence. Okay, but if we increase the number of job to 10, okay, the number of possible solution will be more than 3 million. So it is uh, quite difficult for us to do or to find the solution with minimum average lateness by using manual or random approach like this.